Hi students, and we're continuing our series on relations and functions. So here we've got some main vocabulary points. Independent variable and dependent variable. So an independent variable, this represents the inputs of the relation. The x-axis represents the independent variable. So your inputs are always on the x-axis. Your dependent variable represents the outputs of the relation, and the y-axis represents the dependent variable. So let's take a look at a relation here. Now this relation is a special case because it's also a function. We're going to take a look at the distinction of that in a moment here. So let's have y is equal to 3x squared minus 2x plus 1. So we're interested in this not as something that we can factor, but simply as looking at the input-output relationship here. So we're saying that y is the exact same as this. So what we have is the 3x squared minus 2x plus 1 represents a rule. And this is a rule for assigning a value to y. So what we have here is these x values, these represent your input values. So you are free to choose whichever values you want for x, and then y's value is dependent on what you choose for x. So this is your output value. So for instance, let's say that I let x be equal to 3. Okay, so we're going to say let x equal 3. Well, we want to know what y then has to equal. So it would be 3 times 3 squared minus 2 times 3 plus 1. So what we see here is when x is 3, we get a y value of 22. So we can have an ordered pair saying that 3 comma 22 lies on the graph of y is equal to 3x squared minus 2x plus 1. We can also say that this point, 3 comma 22, is a solution to our function y is equal to 3x squared minus 2x plus 1. So these are all different ways of representing the same idea. The main points to get here is that you have input values and output values. Now your output or your dependent variable isn't always necessarily on its own. Later on, we can see equations like this. So 2x plus 3y is equal to 5. Here, even though y is not isolated and x shares the same side as y, x still represents your input value and y still represents your output. So whenever you see x and y, they're fixed to those ideas of input-output. X in 99% of your cases is going to be an input, and y in 99% of your cases is going to be an output. So let's take a look at an example here where we use input and output to help us solve a problem. So here we've got a sequence of shapes. So you've got a square, you've got 2 squares joined, 3 squares joined. We're interested in the perimeter of this sequence of shapes. So I'm interested in each individual shape's perimeter, but also, like for instance, what would the 50th shape's perimeter be? What the 100th shape's perimeter be? So how is the perimeter of each shape related to the sequence of shapes that's generated? So we're going to start out here. X and y, we might sometimes use different values for inputs and outputs. So I'm going to let n denote which shape in the sequence, right? So let n denote which shape in the sequence we're talking about. So for instance, the first, the second, the third shape. So n you can think of as like which number are we talking about. and we're going to let P denote the perimeter of the nth shape. So in this case here, because P depends on which shape we're talking about, P is our dependent variable, and that's why I've got it coming second here, and N is our independent variable, so we can independently choose which shape we're talking about. So let's take a look at getting some data here. So what we're going to do is we're going to assume that these are squares, so all their sides are equal. And we're going to say that they're unit squares, so they're all of length 1. So the perimeter of our first shape, well, the first shape has a perimeter of 4. Our second shape has a perimeter of, well, 1, 2, 3, 4, 5, 6. We don't count this middle side because it's not a perimeter. It's not part of the exterior, it's part of the interior. So this has 6. So I want you to pause the video and tell me what the perimeter of this third shape will be. So what we find for our third shape is 8. So 1, 2, 3, 4, 5, 6, 7, 8. So what we want to do now is we're going to graph each one of these pairs of numbers as ordered pairs. So let's take a look at how we can do this. I'm going to let this vertical axis represent our positive y-axis. Okay, this is our positive output axis. So what we're going to think of is this is the origin right here. So remember we talked about, you can talk about different points or different sections of the Cartesian plane. Well, we're going to take a look at this graph as just being quadrant 1 alone. So here I've got the point 0, so this is 1, this is 2, and so on. And here is my independent variable axis, my x-axis. In this case, it's our n-axis, and this is going to be 1, 2, 3, and so on. So what we're going to do is we're going to graph out each one of these coordinates onto our graph. So pause the video and give that a shot. So what we've got here is our 3 data points, 1, 4, 2, 6, 3, 8. And, well, notice that they look like they all lie on one straight line. So I'm going to draw a straight line through these. So what we can see here is this straight line represents the data for what we call all of the values, so all the continuous values. So for instance, this sequence only works for whole numbers, but this line shows, well, what if we continued the pattern and somehow had, fractional values in between? So the idea here is we want to see, well, what's the value of 4 that's predicted? Well, we can see here that this arrow here touches 10. And, well, does that fit our pattern? So we're going to take a look now at confirming this result. So the first thing that we want to do here is we want to confirm that this fourth shape does indeed have a perimeter of 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we can confirm that this does indeed have a perimeter of 10. So if we take a look back at our function here, what we saw is that this represents kind of this linear straight line. So what's the rule that created that line? What is the equation for writing that? So there's actually a really neat trick for finding out the equation for what we call linear functions. And the nice thing is it always works. You're guaranteed. So let's take a look at that. So what we have here is a linear equation always has the form y is equal to the common difference times x plus the 0th output. So the common difference is if n increases by 1, then what does p increase by? Or to put it in terms of x and y, or input-output, if your input increases by 1, then what value does your output change by? Okay, so the idea here is that our common difference here is 2. Now what about the 0th output? Okay, so we've got the first output, second output, third output, fourth output. Well, how can we get the 0th output? Well, take a look here. Is that if I'm going down this list, I'm adding 2, so each time n gets bigger, I add 2. What happens if I go up the list? Well, I do the opposite. I take away 2. So the idea here is that to get the 0th term, all that I have to do is take away the common difference from your first term. So in this case, we get 2. So let's write out what the equation is going to be. So what we find in this case is the generating function is y is equal to 2x plus 2. So the idea is the common difference is 2, and my 0th term is 2. So let's check to see that this matches our data. So if I say, let x equal 4, will I indeed get 10 out of it? So I would get y is equal to 2 times 4 plus 2. So y is equal to 8 plus 2, which gives you 10. So the idea is this function generates this list and describes this sequence and also represents this graph. So this tiny little function here gives us all of this information. That's why they're powerful. So in our next video, we're going to take a look at the distinction between functions and relations.